All right, so let's take a look at section 10.2 today, polar coordinates. These things become incredibly useful in Calc 3 as an alternate way of describing the XY plane. All right, so remember that when we talk about Cartesian coordinates, so Cartesian coordinates are our favorite way of describing the XY plane. We've got X, Y. If I take a point, well, then I assign to that point two numbers, and those two numbers are the X coordinate and the Y coordinate, which you get by saying how far do you move in the X direction and how far do you move in the Y direction. So those two numbers are just a way of describing your position in the XY plane. The X direction, how far in the X, how far in the Y. And polar coordinates are just a different way of describing where you are in the XY plane. So, for instance, here's another way of taking this point and giving it two numbers. We're not going to call them X and Y anymore. We're going to call them R and theta. So R and theta. So R in polar coordinates is just the distance to the origin. And so R is the distance from my point to the origin, and theta is the angle that this line segment makes with the positive x-axis. So notice that if I take any point, or any point in space, or in this xy plane, I can assign it an R, how far out it is, and a theta, how far around you have to go. Now, and what does it actually take to describe this? I can describe everything. I don't need any negative R values because R is just the distance from the origin. So I really just need R to be positive. We're going to adjust that in a minute, but all that it really takes in order to describe everything. Right? So we just need R to be bigger than or equal to 0. And less than infinity. And theta, all that I need is theta is between 0 and 2 pi. Because I just need to go around the circle one time. If I go around the circle one time, and I allow my R to be anything I want, that gets me the entire xy plane out of those two things. We don't need to include the equals here because theta equals 2 pi is the same thing as theta equals 0, since that theta is that angle moving out. Now, that said, we're going to allow R and theta to be anything. All right, so if I have an angle, theta, that is bigger than 2 pi, well, that just means that I went around the circle and then I kept on going. Right? So if I had theta equal 4 pi, well, that's the same thing as theta equals 2 pi. If I had theta equals a negative angle, that means move clockwise rather than counterclockwise. So negative theta means this is my theta instead, this direction. I go clockwise rather than counterclockwise. Negative R, we're also going to allow negative R. Right? So if I had something like this, how about the point R theta is equal to negative 1 pi over 4. So R is the distance from the origin, but now that it's negative, so let's think about pi over 4 first. Pi over 4 means that the angle is the angle pi over 4, which is 45 degrees. So this is pi over 4. So if I had 1 pi over 4, let's start with that. 1 pi over 4 would be this point right here, where this distance is 1 and this angle is pi over 4. And so this is 1 pi over 4 in polar coordinates. Negative 1 pi over 4 means rather than move out from the origin along that line, we're just going to move on the opposite line. So this is going to be negative 1 pi over 4. But notice we have another way of describing that. We could equally well have described that in polar coordinates by saying that the angle is actually, so here's pi, and then we have another pi over 4. So that's actually 5 pi over 4 if we went all the way around. From here around, with 4 pi over 4 to make pi, and then another pi over 4 to make 5 pi over 4, and the distance from the origin is 1. So by allowing our r and theta to be anything we want, we have different ways of describing the same point. These 2 points in polar coordinates are the same point. All right, now, that said, it's important to be able to transfer back and forth between the two coordinate systems. So, for instance, suppose that I have the point over here, which in terms of xy is 3, 2. So suppose that we went down here, we had 3 up, and then 3 across, and then 2 up. So this is the point 3, 2. What are the polar coordinate equivalent description? What is the polar coordinate equivalent description of this point? Well, we can do a couple of things, right? So how can I get r? R is the distance to the origin, which according to the Pythagorean theorem is the square root of x squared plus y squared. So r squared is always x squared plus y squared, no matter what. Right, so this, if this is r, this is x, this is y, x squared plus y squared is r squared, and that gets me a way to figure out what r is. R is the square root of x squared plus y squared, which is going to be the square root of 9 plus 4, which is the square root of 13. So that's r. So what else do we need? We need theta. Now we have to be a little bit careful. Theta in this instance, if I took the tangent of theta, I get y over x. Right, so tangent of theta is y over x. At least in this picture, we're going to be a little bit careful here. We have to sometimes be careful with what we're doing. But tangent of this theta is y over x. So theta is tan inverse for this particular problem is tan inverse of y is 2 and x is 3, so 2/3. And whatever that value is, that's our theta. So our r theta description of this point is square root of 13 tan inverse 2/3. Now, what if my angle were somewhere else? And so, for instance, suppose that we were over here, and this is theta. So now this is x, and this is y. If this is theta, well, now it's a little bit harder to see what's going on, right? Because if I take the tangent of theta, well, that's not actually anywhere in my triangle. But we can still do, we can still actually work out what we need to work out. Because in this picture, tan inverse of y over x, if I took y over x and took tan inverse, I'd get the angle that we need in here. So what we actually have here is tan inverse of y over x. It's not exactly the angle that we're looking for, right? It's this angle. So we need actually pi minus this to get to theta. So sometimes you have to do some adjustments, right? Because pi is the whole way through. I need to subtract that angle, and that's what would give me theta. So we have to be a little bit careful, but that's the basic idea. Now, what else? Suppose that I asked you to go the other order. If I give you polar coordinates, suppose that I said, let's look at this polar coordinates, pi over 3 and 2. So 2 pi over 3 in r theta. What are x and y? That's the question. So what are x and y? Well, so I have r, I have theta. Cosine of theta is x over r, which means that x is r cosine theta. And that's true actually no matter where our picture is. No matter where we draw this, x is always r cosine theta. And in a similar fashion, y is r sine theta. Because if I took the sine of theta, I'd get the opposite over r, which is y. So sine of theta is y over r. So y is r sine theta. Right? And this gets me an easy way to transfer any r theta into x and y. So in this case, x is 2 cosine pi over 3, and y is 2 sine pi over 3. And so we can use these formulas to go back and forth between either of the coordinate systems, Cartesian or polar. Okay, so let's think about some basic equations in polar coordinates. So for instance, if I said, show me on the xy plane, on the axis system, if I said, what are all points which have r equal to 2? Any point which has r equal to 2. Well, r is the distance from the origin, and so if I want all points which are 2 units away from the origin, I get a circle. So the equation of a circle in polar coordinates is very simple. R equals 2, as compared to x squared plus y squared equals 4 in Cartesian coordinates. So that's one powerful aspect of polar coordinates. If we're working with circles and we transfer everything to polar coordinates, then our equations of the circles are much simpler and much easier to work with. So this is r equal to 2. What if we had a fixed theta? Suppose that I said theta equals pi over 6. All points which have theta equal pi over 6. Well, if theta is equal to pi over 6, theta is the angle that we move up. So I want all points which have an angle of pi over 6 when we move up. Well, that's a line. Everything that's on this line makes an angle of pi over 6 with the x-axis. It's not the entire line. It does not go down into the third quadrant, because down here the angle is different. But it's this half of the line that's in the first quadrant for this particular angle. So this is a line. Okay. So that's all we need to say at this point about polar coordinates. And we'll see you next time.